Yeah, good evening everyone. Extremely sorry for the delay. I had some technical glitches here. So let's start the class today. So are you able to hear me?
Yes, I can.
Thank you. So let me share the screen. So this is the last week session. So is the screen visible? Is the screen visible for everyone?
Yes, ma'am.
Yes.
So let's begin with the first problem. Here we have given a non-singular matrix A and given that lambda is an eigenvalue of this matrix A. So the question is to find the eigenvalue of not to find all eigenvalue. What is the possible eigenvalue of this adjoint of A? So let us see. Here A has eigenvalue lambda. We know that A inverse of A equal to adjoint of A by determinant of A. So this is one of the basic results we already know. Okay. So before going to prove this, let me give you two results. Okay. First result. If A is a non-singular matrix, and lambda is an eigenvalue of A, then of course since A is non-singular and lambda is eigenvalue of A means this lambda cannot be 0. Lambda is a non-zero value. So 1 by lambda exists. Okay. And this 1 by lambda will be an eigenvalue of the
A inverse.
A inverse. Yes. So any of you want the proof of this result, or do you know the proof?
No. Yes.
Want the proof?
We know the proof. No.
Okay.
We know the proof.
Okay. If anyone wants, you can tell. Otherwise, let me go to the other result. Next result. Okay. Result 2. If A has eigenvalue lambda, then Ka, where K is any scalar, Ka is again a matrix. This matrix Ka has eigenvalue K lambda. Is this okay, this result? Any doubt in this result? Or you want the proof?
It's okay.
Okay. So, using these two results, we will prove this problem. We will solve this problem. So, what we already know is A inverse is adjoint of A by determinant of A. A inverse equal to adjoint of A by determinant of A. What this means is we can write as adjoint of A equal to determinant of A into A inverse. So in the question, what we have given is A has eigenvalue lambda. So what is the eigenvalue of A inverse?
Lambda inverse.
Yes.
Monomer lambda.
Eigenvalue of A is lambda. So eigenvalue of A inverse is lambda inverse or 1 by lambda. Okay. So what is the eigenvalue of adjoint of A? Adjoint of A, determinant of A into A inverse. What will be it? Determinant of A is a scalar and we know the eigenvalue of A inverse. using the result to what we can say?
Determinant of A upon lambda. Determinant of A upon lambda.
Yeah, determinant of A over lambda. So this is the eigenvalue of adjoint of A. Okay. So the answer is determinant of A over lambda, the first option A. Okay. Is this clear? Anyone is having doubt here in the question?
No.
Any? Yeah. If you have doubt, you can ask now. Or let's move to the next problem. Okay. Here, it is given that two statements. The first statement says that A and B are two invertible matrices. Then AB and BA have same characteristic roots. So we have to check whether this statement is true or not. Let us go. So what is your guess? Any guess whether it is true or not?
Ma'am, AB and BA may or may not be equal, no?
AB and BA may or may not be equal. We are not saying this is equal. The question is whether they are having same characteristic root or same characteristic polynomial.
So it will vary, no? It may vary, characteristics root.
Okay, for different matrices, characteristic root will be different. But what about if two similar matrices? If any two similar matrices I am taking, so whether they have same characteristic root or not?
Similar matrices have same characteristic.
Yes. So let us see whether this AB and BA are similar or not. So I am writing this BA as A inverse A. That means I am writing, I am just multiplying with the identity. Okay. IBA. So whatever the order corresponding identity I am using. So this I can write as A inverse A. Instead of identity, I am writing A inverse of A into BA. So what we are getting is A inverse AB A, and A is non-singular. It is given A is A and B are two invertible matrices. So A is non-singular. So what we are getting is there exists A such that A invertible and BA equals A inverse AB A. So what does this means? This last sentence.
BA is similar to AB. BA is similar to AB.
BA is similar to AB. Okay? AB
Yes.
and BA are similar. So AB and BA are similar means they have same characteristic root, that is same characteristic polynomial also, right?
Yes.
Yeah. So AB and BA have same characteristic polynomial roots.
In that case, AB must be a diagonal matrix, isn't it?
AB and BA.
Ma'am?
No, this need not be diagonal matrix.
It is not diagonalizable.
It can be any matrix. Whatever the matrix,
Okay.
AB and BA will be similar. Okay. So, okay. Anyone wants the proof that if A and B are similar, then their characteristic polynomial both are same?
Yes, ma'am.
Okay. So let us see. Okay. In the case of AB and BA, we will take the case itself. Or in general, AB are similar, then characteristic polynomial of A and B are same. So since A and B are similar, we can write B equals P inverse AP. Okay. So determinant of B minus XA I am considering, which is equals determinant of, instead of B I am writing P inverse AP. Okay. And instead of phi I am writing X P inverse P. P inverse P is the identity matrix. So from here I can write it as this P inverse I am taking to the left side. P inverse and A minus Xi here I am taking, and P I am taking to right side. Okay. So determinant I can, using the property of determinant, I can write it as determinant of P inverse, determinant of A minus Xi, and determinant of P. And determinant of P inverse and determinant of P will be cancelled because one is the inverse of the other. Okay. So this I can write determinant of A minus Xi. Okay. So determinant of B minus Xi and determinant of A minus Xi are same. That means this is the first one is the characteristic polynomial for the matrix B, and determinant of A minus Xi is the characteristic polynomial for the matrix A. So these both polynomials are same. So their corresponding roots. That means our characteristic value or eigenvalue are both are same for A and B. Is this okay?
Yeah. Okay.
Okay. So let's go to the next problem. So here given a square matrix A, which is given, okay, A is given. So it is a symmetric, real symmetric matrix. So the question is about the eigenvalues, whether it is real, positive, negative, and so on and so on. So this actually you have already seen in the class, the proof and everything. If A is a real symmetric matrix, what will be the eigenvalues?
Real and positive. Always real.
Which one?
Always right.
Always real.
A. Always real. Always real.
Yeah, always real. This I am not going to repeat the proof, already proved in the class. So let us just examine all other three, A, C and D, whether it is possible or not. So if I am taking a matrix A equals 1, 0, 0, minus 1. So what are the eigenvalues of A? Anyone?
1 minus 1.
Yeah, 1 and minus 1. A is a diagonal matrix. For a diagonal matrix, we can easily say the diagonal entries are the eigenvalues. So 1 and minus 1. So from this example, also we can say A transpose equals A. See, A transpose will be same as 1, 0, 0, minus 1. So these are same. So A is a real symmetric matrix, but the eigenvalues are 1 and minus 1. So this is a counter example for the option A. That is, it is a negative value. Eigenvalue takes a negative also. Also, this option C also false because it takes a negative value. D also in the same way it is false. Okay. So only thing is, if A is real and symmetric, it is eigenvalues are always real. Is this okay?
Okay, ma'am.
Okay, ma'am.
So let's go to the next problem. Here it is given that A is an idempotent matrix. So the question is to find the eigenvalues of the idempotent matrix. So do you know what is idempotent matrix?
A square is equal to A.
Square equal to
A square equal to A. A square matrix, the definition is said to be idempotent if A square equals A. Okay. So we need to find for an idempotent matrix what are all the possible eigenvalues. So the only condition we are having is A square equal to A. Suppose lambda is an eigenvalue of A. So what we can write if we are supposing lambda is an eigenvalue, then what is the condition we have? Then will we say this lambda is an eigenvalue of A? I'm just asking for the definition, like if a positive or if any
S square.
constant. Yeah. So the definition, by definition, if lambda is an eigenvalue of A, we can say there exists x not equal to 0, x should be a non-zero vector such that Ax equals lambda x. Okay?
Yeah.
Yeah. Now we will consider A square x. A square x we can write as Ax. Right? Now what we can write from this step?
Lambda square x.
Yeah. Okay, stepwise we will write. This Ax is lambda x. So we will get A of lambda x. A of lambda x means lambda times Ax. Again Ax is lambda x. So we will get lambda of lambda x. Equals lambda x or lambda square x. And also we know that since A is idempotent, A square equals A. So what we can write here? A square x equals Ax. For the same x we are writing A square x equal to Ax. Okay, this is clear?
Yeah.
And what is this Ax from this equation?
Lambda x, ma'am.
Lambda x.
Ax is lambda x. So we get A square x equal to lambda square x and A square x equals lambda x. So we are equating lambda square x equals lambda x. Okay. That means lambda square minus lambda of x equals 0. So from this what we can conclude? Next step.
So lambda is equal to what? Lambda is equal to 1 or lambda is equal to 0?
Yes, lambda square minus first lambda square minus lambda equals 0. The
0.
reason is x not equal to 0.
X not equal to 0.
Yeah, if x equal to 0, we cannot write it as 0. We know that x is an eigenvector, so it is not equal to 0. So this is lambda into lambda minus 1 equal to 0 implies lambda equals 1 or lambda equal to 0. Either 1 or 0 is possible. So we are starting with a lambda is an eigenvalue, right? Lambda is an eigenvalue. Suppose lambda is an eigenvalue. So we will get lambda equal to 0 and lambda equals 1. Okay, is this clear?
Yes, ma'am.
Yes.
Conclusion is 0 and 1 are possible values of eigenvalues of idempotent matrix. So let me ask one question. So is this necessary that we will have both 0 and 1 for idempotent matrix? Like if I am taking a matrix A which is idempotent, so is this possible A has only 0 as the eigenvalue or only 1 as the eigenvalue? Any idea?
Mm,
No, madam.
It is not okay. Let me check. I am taking A equals 0, 0, 0, 0. Is this A idempotent?
Yes, ma'am. A square equals to
Yeah. Then what are all the eigenvalues of A?
0.
0
0.
only. Here 1 is not an eigenvalue. Okay. Now if I am taking A equals 1 0 0 1, our identity matrix. Again A square is A, right?
Yeah.
Okay. So here what is the eigenvalue?
1.
1. Yeah. So we are getting one idempotent matrix which is having only 0 as eigenvalue and another idempotent matrix which is having only 1 as the eigenvalue. So in the above problem, what we are saying is the possibility is 0 and 1. Only 0 is possible, only 1 is possible. Also both 0 and 1 are also possible. Let us see. B equals 1 0 0 0. What is B square? 1 0 0 0, right? Okay.
Yeah.
So what
Okay,
are all
ma'am.
the eigenvalues here?
1.
1 and 0, right?
1 and 0.
Yeah. So here both 1 and 0 are coming for this idempotent matrix. Only 1 is coming. Here only 0 is coming. Okay.
Okay, ma'am.
Yeah. So any doubt here in the question, last question?
No, ma'am.
Okay. Now let us go to the next problem. Here the question is, okay, by the way, I think I missed one question here. Yeah. Sorry, I missed the question here. Here we have two statements. In the second question, we have two statements. If A and B are two invertible matrices, then A, B and B A have same characteristic root. That we proved this statement is true, right? This is true. So I think
Yes, ma'am.
we didn't check about this statement too, right? Okay. Here the statement is, if lambda is an eigenvalue of algebraic multiplicity R of the matrix A, then we need to prove that 0 is an eigenvalue of algebraic multiplicity R of A minus lambda again. So the question is not to prove whether it is true or false. So what is your guess whether it can be true or not? Idea, if A has a eigenvalue lambda of multiplicity R, then A minus lambda in whether this matrix has 0 as an eigenvalue with algebraic multiplicity F. This is the question. Okay, let us see. I am considering determinant of A minus lambda I. I am considering the characteristic polynomial of A minus xi. So, what we have given is lambda is a root of the characteristic polynomial. That means it is an eigenvalue, means it is a root. So, how can we write it as in terms of lambda? Lambda and some other polynomial. How can we write it as this polynomial? Lambda is a root means x minus lambda is a factor, right? How many times this x minus lambda will occur? Lambda is
R.
R times,
yeah,
ma'am.
it is
R
the root
times.
of multiplicity R. So x minus lambda power R into some p of x will be here. Okay. Where? Okay, what about p of lambda? Is this 0 or non-zero?
Not equal 0.
Yeah, not equal to 0 because R is the multiplicity.
Or
So
is
in the remaining
yes.
factor, lambda will not be a root. So p of lambda is not equal to 0. Okay. Now consider B. So our question is for A minus lambda I. Whether 0 is a algebraic multiplicity, 0 is a eigenvalue of algebraic multiplicity or in A minus lambda I. That is the question. So again, I am taking B as A minus lambda I. So I am considering the characteristic polynomial B minus xi. Okay. So how can I write it? B is A minus lambda I. So this is A minus lambda I minus xi, which is determinant of A minus lambda plus xi. Okay. Let y equals lambda plus x. Instead of this lambda plus x, I am giving y. So what I can write is determinant of b minus xi equals determinant of a minus yi. Okay. So we have determinant of a minus xi is x minus lambda power r into p of x. So any doubt in between?
Many questions.
Yes. Can you be a bit Excuse me, are you asking something?
Screen is not seen. Screen is not visible.
Okay, let me continue. The screen is visible now, right?
Yeah, now it is okay.
Yes, sir.
So, determinant of b minus xi is determinant of a minus yi. Then, what is determinant of a minus yi? How can we write it as using equation 1? This is the
X
Y
equation.
minus lambda.
Yeah.
y minus lambda raised to r.
Y minus
Is y.
Yeah.
I am replacing this y with the term lambda plus x.
అంటే x అనేది ప్రైమ్ నెంబర్ అయితే x అనేది ఆడ్ నెంబర్ x has exactly 2 divisors x కి
If somebody is speaking, can you please mute your microphone?
a alone is sufficient but అంత చూడే x has తన అలాగే ఉంటాం ఆడ్ నెంబర్ అయి ఉంది ఎగ్జాక్ట్ గా 2 divisors ఉంటాయంట.
So, we will get instead of y, I am giving lambda plus x minus lambda all power r into p of lambda plus x. Okay, what is this? X power r p of lambda plus x. Now I am writing it as x power r into q of x. So instead of p of lambda plus x, I am writing this polynomial as q of x. Okay. So what does this means? Determinant of b minus xi is x power r into q of x. This is the characteristic equation for b, the matrix b. We are getting it as x power r into q of x. Now, is x equal to 0 is a eigenvalue?
It is x minus r, x minus 0 raised to r.
Yeah, this is x power r means x minus 0 raised to r. That means 0 is a root of this equation, right?
Yes.
X equal to 0 is a eigenvalue. So what is the order of this root? What is the order of x equal to 0 in this polynomial?
R.
R. Okay. From this equation we can say r is the root, but we need to check whether q of this 0 is 0 or non-zero. What is q of 0? Q of 0 means p of lambda plus 0, right? Which is p of lambda. Is this 0 or non-zero? that we already seen in the
Non-zero.
Non-zero.
because lambda is a eigenvalue of A of order R. So this is non-zero. So what we are getting is this characteristic equation we have written in terms of x power R into q of x with this 0 is not a root of q of x. So x equal to 0 is an eigenvalue with the algebraic multiplicity R. Okay. So our statement is true. So statement is true. So both the statement are here true. Is that clear for everyone?
Yes, ma'am.
Okay. So let us go to the next problem. Here the question is to find the algebraic and geometric multiplicity of the given matrix. Let me write the matrix as 2, 1, 4. So determinant of P minus xi equal to 3 minus x, 2, 1, 4 minus x. So we are doing A minus x times identity matrix. So what is this value? 3 minus x into 4 minus x minus 2 is equal to 12 minus 7x plus x square minus 2. Okay. So what are all the roots of this equation? We can write it as x minus 5 into x minus 2, right? X square minus 7x plus 10. Okay. So
Okay.
Okay, ma'am.
None.
No, ma'am.
okay. So what are all the eigen values here?
Five and 2.
5 and 2. What is the algebraic multiplicity of 5?
1.
1. And algebraic multiplicity of 2?
1, ma'am. 1.
Yeah. What is geometric multiplicity of 5?
So to find out eigenvectors first, no? For this.
Excuse me. Please repeat.
So to find out eigenvectors for lambda is equal to 5.
Question is to find algebraic and geometric multiplicity.
I mean to say for geometric multiplicity, we have to find out the eigenvectors first, no?
Yeah. No. Geometric multiplicity for eigenvalues. Both algebraic multiplicity and geometric multiplicity are for eigenvalues. Okay. We have one relation. In the class, sir already talked about this. For any lambda, whatever the lambda means any eigenvalue, this geometric multiplicity will be less than or equal to algebraic multiplicity, and this will be geometric multiplicity will be greater than or equal to 1. So here geometric multiplicity of 5 is less than or equal to algebraic multiplicity of 5, which is 1. So what is geometric multiplicity here?
1 only.
1. In the same way, 1 less than or equal to geometric multiplicity of 2 less than or equal to algebraic multiplicity of 2, which is given as 1. Okay. So what is geometric multiplicity of 2? 1, right?
That is also 1, yes.
Okay. So what actually geometric multiplicity? So we know algebraic multiplicity is the how many times that is a factor, like how x minus lambda power r. We have lambda is an eigenvalue and we have a factor x minus lambda power r. Then r is the algebraic multiplicity of lambda. So geometric multiplicity means corresponding to lambda we have a characteristic vector space, a subspace. the dimension of that subspace is the geometric multiplicity. So this geometric multiplicity also we will find it for a eigen value. Okay. Any doubt here?
Here it is okay because here it is algebraic multiplicity is 1. That's why we need not calculate for geometric multiplicity.
Yeah.
But in case algebraic multiplicity is greater than 1, more than 1, then you have to determine the vector eigenvector, no?
Yes.
In that case.
Okay, if algebraic multiplicity is greater than 1, say if algebraic multiplicity some lambda is some 2 or something, then geometric multiplicity can be either 1 or 2. So
yes,
what we need to do is we should find a minus lambda I.
Yeah.
Yeah. Then the corresponding eigenspace of a minus lambda I, corresponding eigenspace of lambda.
Yes.
The corresponding eigenspace, or we have two linearly independent eigenvector corresponding to lambda, then geometric multiplicity will be 2. Okay.
Yes.
If we have only one eigenvector, linearly independent eigenvector corresponding to this lambda, then we have geometric multiplicity equal to 1.
1.
Okay.
Yes.
Yeah, that is how we usually find. Like we need to find the space and what are all the eigenvector corresponding to one eigenvalue, and to find the possible linearly independent eigenvectors. And the number of linearly independent eigenvectors corresponding to lambda is the geometric multiplicity. So in general, we can find this. Here, this is a very easy case because we get this both of the algebraic multiplicity of both the eigenvalues are 1. That is, that's why we are concluding it easily. Okay. So, anyone has doubt here? Any other doubt?
Hello, ma'am.
Yes.
Answer is 1, 1.
Answer. Yeah, 1, 1. Because we got both algebraic multiplicity and geometric multiplicity as 1.
Okay, ma'am. Thank you, ma'am.
Okay. Okay. Now let us move to the next problem. So here a matrix A, 2 by 2 matrix is given. It has eigenvalue 1 and 2. The question is to find the eigenvalues of A square plus 2A. So we already have one result. If A has eigenvalue lambda, Ka has eigenvalue K lambda. That we already see. In the same way, we have one more result. If A power n, if A has eigenvalue, if A's eigenvalue is lambda, then A power n, its eigenvalue will be, one of the eigenvalue will be lambda power n. So this result is very easy to verify. A has eigenvalue lambda means there exists a non-zero x such that Ax equals lambda x. Okay. In the case n equal to 2, what I am considering is A square x. That means A of Ax. Here Ax equals lambda x. This is A times lambda x. We can take lambda outside and again Ax. So this Ax is again a lambda x. So we will get lambda square x. Okay. In the same way, we can write A power n of x as A power n minus 1 of A of x, which is A power n minus 1 of lambda x. Again, A power n minus 2. Here lambda we will get outside Ax. This is equals lambda square into A power n minus 2 of x. So if we are continuing in this way, what we will finally get is lambda power n into x. So from here, what we are getting is there exists a non-zero x such that A power n x equals lambda power n x. That implies lambda power n is an eigenvalue of a power n. So, in the question, we need to find the eigenvalues of a square plus 2a. So, we have for a square, we have lambda square as eigenvalue. Okay. 2a, we have 2 lambda as eigenvalue. So, we can easily guess lambda square plus 2 lambda will be an eigenvalue for a square plus 2a. So, let us check this condition. A square plus 2a of x. So, this x we have already chosen x non-zero, which is satisfying this condition, right? So, a square plus 2a of x, what we will get? A square x plus 2ax. So, what is this? What is the value of this one?
Lambda square x.
Yeah, lambda square x
Plus 2 lambda x.
2
2
lambda x.
lambda x.
That means lambda square plus 2 lambda x. Okay. That means for this matrix a square plus 2a, we have a non-zero x such that a square plus 2ax equals lambda square plus 2 lambda x. That means lambda square plus 2 lambda eigenvalue of a square plus 2a. So for a, we already have two eigenvalues given 1 and 2, right?
Yes, ma'am.
So what are the value of lambda square plus 2 lambda here?
One plus two.
Lambda is
And 4
1
plus
and 2. Yeah,
1 plus 2, that is 3.
1 plus 2 and
And
plus
4 plus 4, 8.
4 plus
yeah,
4.
4 plus 4. So 3 and 8 are the eigenvalues. Okay. Also, these are the only two eigenvalues because A is a 2 by 2 matrix. So A square plus 2A is again a 2 by 2 matrix. So maximum two distinct eigenvalues. That is for the characteristic polynomial, maximum two distinct root can be there, right? So this A square plus 2A have maximum two eigenvalues. So thus we get 3 and 8 are the eigenvalues. Is the problem clear for everyone?
Yeah.
Okay.
Yes, ma'am.
Now let's go to the next problem. Okay. So the question is given A matrix. It is a 4 by 4 matrix. So under what condition on A, B and C this A is diagonalizable? We need to find the value of A, B and C such that this matrix A is diagonalizable. Okay. So for that, first we will start with the characteristic equation. So determinant of, let me write it, xi minus a. Okay. So what will be it? X time identity minus a. 0 minus a, x0, 0. 0 minus b, x0, 0, 0 minus c, x. Okay. I am just writing xi minus a matrix. So I am finding the determinant. What is the determinant of xi minus a? This is a diagonal matrix, so determinant, what will be it? It is very easy to find the determinant for a diagonal matrix, right?
X is to 4.
Yeah, x power 4. We just need to multiply the, all other terms will be going to 0. So x power 4 is the, so this is our characteristic polynomial or equation, right? So what are all the characteristic roots?
0.
Yeah, x equal to 0 is the only eigenvalue. Okay. So the question is, we need this A to be a diagonalizable matrix, right? So the eigenspace corresponding to 0 should be of dimension. What should be the dimension? Yeah. Saying something. Anyone else? Whether done?
Is it 4?
Eigenspace corresponding to 0 have dimension 4, right? Is this fine everyone? Anyone has doubt?
Ma'am, this power 4, how did you get, ma'am?
Can you explain? Yeah, someone was asking some doubt.
Ma'am, this determinant value of the diagonal matrix. How did you get this x power 4?
Okay, this determinant. Yeah, determinant, how we will find the determinant? First we will take the first element x here. Then find the determinant of this one. Okay. Then see x into determinant of x0 0 minus b x0 0 minus c x. Then next one is minus 0 into this matrix minus a 0 0 0 x0 0 minus c x. So anyhow whatever the matrix here, this will be the 0 term because we are multiplying with 0. So next term also again we will multiply with 0, that term will also go. Again we will multiply with 0, that term will also go 0. So the only thing is here we have x into this submatrix 3 by 3 matrix. Again this 3 by 3 matrix we are repeating the same procedure. Here we have x into, again we have one x here, x into the determinant of this submatrix. All other will be going to 0 because this is 0, this is 0. So we will get x into x0 minus c x, right? Here it is x square into, this determinant is x square minus 0 x square, which is x power 4.
Okay, ma'am, got one.
Okay. So is this clear? Eigenspace corresponding to 0 have dimension 4? Any doubt here? In the last sentence? Okay, if you have any doubt, you can ask here because here we are taking the matrix A to be diagonalizable. So the total eigenspace should be the dimension of eigenspace should be the dimension of the whole space. Here it is 4. So it should be 4. Okay. This corresponding to 0, the eigenspace is dimension 4 means dimension of A minus 0y. This is the eigenspace, means dimension. null space. Okay. This should be 4. See, dimension 4 means the null space of A minus 0i should be 4. Is this clear? Our aim is to find if for some characteristic value A minus xi, that is A minus lambda I, that is Ax equals lambda x, or A minus lambda I of x equals 0. Okay, that means x belongs to the null space of A minus lambda I. Ax equals 0x. This is what we want because 0 is the eigenvalue. So, A minus 0 times I of x should be equal to 0. Ax equal to 0. So, we want set of all x such that Ax equal to 0 should have dimension 4. So, all x such that Ax equal to 0 should have dimension 4. That is what we are writing. Null space of A is 4. Okay.
Okay, ma'am.
When will be the null space of A is 4? What should be the value of A, B, C?
0 na ma'am.
Yeah, 0. We have rank A plus nullity of A equals 4, right? And rank A, here nullity of A is 4. Rank A plus nullity of A is 4 means rank A should be 0. So, in order for rank to be 0, all the value A, B and C should be 0. Then only the rank of this matrix will be 0. Okay. Is the question answer clear for everyone? Any doubts here? Any doubts? So let's do one more problem, I think, then we will stop. So we need to prove this is diagonalizable. So for this, where we will start with the characteristic equation again. Determinant of xi minus a equal to 0. So first we will find the eigenvalues and then the corresponding eigenvectors, and then we will check what is the corresponding dimension of the corresponding characteristic space corresponding to each eigenvector. Okay. For that we need to find the characteristic equation. Writing the characteristic equation, this is x minus 1 square minus 1. Okay, what are all the eigenvalues of
equal
A?
to 0 and
0 and 2, right? Eigenvalues are 0 and 2. So, eigenvector, okay. From this, can you conclude whether it is diagonalizable or not? I am just getting the eigenvalues. So, is this diagonalizable or not?
Diagonalizable.
Yes, because we are getting this algebraic multiplicity 0. So, algebraic multiplicity 1 for each 0 and 2. And geometric multiplicity also will be 1 for each 0 and 2. So, corresponding to 0, there exists one linearly independent eigenvector, and corresponding to 2, there exists another linearly independent eigenvector. So, these two linearly independent eigenvectors together forms the basis. So what we are getting is total dimension is 2. So it will be a, or let me give proper explanation. So let us see eigenvector corresponding to x equal to 0.
Can we say when A has two different eigenvalues, then A is diagonalizable?
Yeah, because A is 2 matrix here. If A is 3 by 3 matrix, we cannot say if A has two distinct eigenvalue, we cannot say whether it is diagonalizable or not. Here it is 2 by 2 matrix. Corresponding to each eigenvalue, we have two different eigenvectors. So altogether, we have two eigenvectors which are linearly independent, right?
Okay.
So that means it is diagonalizable. Means this 2 means it is the dimension of this A, right?
Okay.
In that case, we can say. Otherwise, if A is 3 by 3 matrix and we have two distinct eigenvalues, say lambda 1 and lambda 2, there is a possibility lambda 1 can have only one linearly independent eigenvector, lambda 2 have one linearly independent eigenvector. So altogether, A is having only two eigenvectors, linearly independent eigenvector. But
Suppose the 3 by 3 matrix have three different eigenvalues.
yeah, in that case, it will be diagonalizable.
Okay, okay.
Yeah.
Okay, madam.
So let me give this eigenvalue corresponding to x equal to 0. That means determinant of A minus xi means only 1, 1, 1, 1 will come. This is our A. Okay. Sorry. But we want to prove that this is our AX equal to, this is our eigenvalue 0, 0, 0. That is 0 into x1, x2. Okay. So this means x1 plus x2 equals 0. Both the equation solving, we will get x1 plus x2 equal to 0 or x1 equals minus x2. Okay. So 1 minus 1. If we are taking 1 minus 1, then the span of 1 minus 1 will be the characteristic space associated with the 0. In the same way, let us find the 1, 1 into x1, x2. 2 is the second value. So the eigenvectors corresponding to 2, we will find it as 2 times x1, x2. Ax equal to 2x. Okay. So x1 plus x2 equals 2x1 and x1 plus x2 equals 2x2. Sorry, 2x1 plus, okay. So solving this, you will get x1 equals x2. So the 1, 1, the span of this is the, because we have only one variable, if we are giving 1 to x1, then x2 will also be 1, right? So this span will be the eigenspace corresponding to 2. Okay. So what we are getting is 1 minus 1 and 1, 1. So these two vectors, we are getting the eigenvector. So we will write this as P. Okay. Now we will find P inverse. P inverse is half means determinant of this 1, 1 minus 1, 1. And our A equal to 1, 1, 1, 1. So P inverse of AP. So this is the formal way of writing this A is diagonalizable. So we will write this, we write this P using the eigenvectors. So we will find the P inverse of AP. So you can just calculate the value of P inverse of AP. So what you will get is 0, 0, 0, 2. So this is a diagonal matrix, and this diagonal entries are the characteristic values. That is, first one is 0 and this is 0 because we are taking the vector eigenvector 1 minus 1 here corresponding to 0. So first vector is corresponding to 0 means this first entry is the corresponding eigenvalue. Here also 1 1 is corresponding to 2, that is why the second entry is 2. So we will get the diagonal. P inverse of AP is a diagonal matrix. So in this way also we can say A is diagonalizable. Is this method clear? This is a bit a calculation.
Yes, ma'am. Yes.
Yeah. You can solve in the earlier way also, just finding the algebraic multiplicity and geometric multiplicity. Okay, let me stop here.
Ma'am, it is 1 by 2 now, last.
P inverse AP.
P inverse AP 0, 0, 0, 1 by 2 now.
I think no. Okay, let me just calculate it here. So AP is 0, 2, 0, right? And P inverse AP half into.
Okay, ma'am, maybe you are correct.
Maybe you are correct.
Oh, yeah, this is correct. You can just check the calculation again. This is 0, 0, 0, 2. Is this okay? This calculation?
Yes, ma'am, correct, ma'am.
Okay. Yeah. Any other doubt?
No, ma'am.
Okay. So I think let's stop the session today. If you have a doubt, you can ask. Otherwise, you can leave the meeting. Thank you everyone for attending the all sessions.
Is this
Thank you,
your
ma'am.
last? Is this your last exam?
Yeah, maybe we will have one revision session also. Maybe in this week before the exam. Exam is on 25th. So before the exam, we may have one revision session.
Okay.
So this problem solving is the last session, the week 8 session. Okay, I'm ending. Yeah, any doubt? Okay, I'm stopping the meeting now.